Hello, everybody. Thanks for being here today. My name is Asaf Chelouche. I'm a software developer at a company called AppsLayer. We're based in Israel. And if you haven't heard about us, we do mobile application marketing technologies, and a big part of our business is the mobile attribution business, where we're the market leader globally. We also have a global presence of 18 offices worldwide from the US, EMEA, and APAC. We're approaching 1,000 employees, and we ingest over 100 billion requests a day. And just to name a few of our clients, so really big clients globally in all kinds of distinct industries. And this pretty much explains the huge number of traffic that we process each day. And today we're going to talk about the origins of Lambda Calculus, its syntax, church numerals, how you do control flow in math in Lambda Calculus, and just a few related topics to top it off. So some of you may have heard about the halting problem. This is an open problem in mathematics back at the beginning of the 20th century. And two people sought to solve that problem. The first one was Alan Turing with his computational machines, and the second person was Alonzo Church. He worked in the United States back in the 1930s on this topic, and he invented Lambda Calculus. And what we should remember is that both Turing machines and Lambda Calculus are equivalent models, meaning they have the same computational power. So why are we here? I think that sometimes if you have context or knowledge of history, you can have a better understanding of the topics which you're dealing with today. It's also a mental exercise, and it's challenging, and I like challenges. And also, there's a lot of fun in it, so it's always nice to do something of this sort. Okay, so let's start away with the syntax of Lambda Calculus. And in Lambda Calculus, we have terms, and terms can be categorized either into variables, applications, or abstractions. We're going to see what each one of those are. So with regards to variables, they can be x, y, z, a, b, c, whatever you want. And if we take this Clojure form, function of x, list x, so we can see x is a variable. And in another example, we see here x and y are variables as well. So nothing out of the ordinary. Most of you already know this kind of things intuitively. Let's talk about abstractions. Abstractions are basically functions with parameters. So here we see a lambda term for an abstraction. So it begins with an opening parentheses, lambda, a list of variables, dot, and the body term, and a closing parentheses. Now, what is this body term? It can be any other lambda term. So in itself, it can be a variable, an abstraction, or an application, which we're going to see in the next slide. And I said earlier that we have after the lambda a list of terms. We can have also no terms, no variables. We can have just lambda dot, which is equivalent to a no parameter function in Clojure. And one more thing, in Lambda Calculus, everything's curried, meaning that all functions are functions of one parameter. So in this case, when we write this term in Lambda Calculus, it's just a shorthand form of writing this explicit term, which is lambda a that returns a lambda b that returns a lambda c with the body term. So again, an example in Clojure, we have a function of a, b, and c, and it just wraps them in a vector. So if we curry it, we get a function of a that returns a function of b that returns a function of c, and then there's the body expression here, the body form. And again, lambda and Lambda Calculus is like function in Clojure. Let's talk about applications. An application, it's just an opening parentheses, a list of lambda terms, and closing parentheses. Applications are left associative in Lambda Calculus, meaning that if we write this, we actually mean this. So here we're applying A on B, we're applying the result of that on C, and we're applying the result of that on D. Okay, so again, an example in Clojure, we have here map inc and a vector. So in Clojure, if I want to left associate an application, I can use partial in order to make a partial application of a function. So here I'm partially applying map on inc, and the result of that is a function that expects a collection or a sequence. So here I'm just applying it on the vector 1, 2, 3. Okay, so why are abstractions right associative and applications are left associative? So let's look at an example in Clojure. So let's say I have the function my plus of the parameters a and b. So let's query it. So now I have this new form of my plus it's a function of a that returns a function of b, and then it just adds a and b together. And here we can see the applications are left associative, the abstractions are right associative, and together they just form up and interlock like gears, which is pretty nice. Okay, so what haven't we seen so far? We talked just about terms and applications and abstractions and all that stuff. So we haven't seen any primitives, we haven't seen any aggregates. So you're probably asking, well, how can we compute or calculate stuff if we don't even have numbers? So the nice thing about inventing something is that you can name it after yourself. And this is what Church did. He invented church numerals. And straight from Rich Hickey's playbook, we're going to look at a dictionary definition. So a church numeral is a figure, symbol, or group of these denoting a number. So let's see some examples of church numerals. So this is the church numeral for the number 0. It's a function of s that returns a function of z that just returns z. What are s? What are z? At this point, I don't care. This is the church numeral for the number 1. It's a function of s that returns a function of z that applies s on z. This is the church numeral for the number 2. Function of s returns a function of z, and it applies s twice. And in general, the number of applications of s is equivalent to a natural number n. And just as convention for this presentation, we're going to denote the nth church numeral by Cn. So let's dive straight in, and we're going to see some basic church numerals. We're going to see a few transformations that I use in order to play around with church numerals because they're functions, and I want to be able to manipulate them more easily. So we're going to see the usage of a few transformation functions from integers to church numerals and vice versa, and from church numerals to their string representations and vice versa. So let's go to the REPL. And here we see an example of C1. It's a function of s that returns a function of z, and it just applies s on z. And if we evaluate this, we just get a Clojure function. We have the transformation functions that I've mentioned earlier here, right here. I'm not gonna dive deep into them. You can see it for yourselves in the code examples in the GitHub repository. So a few more examples. So let's take the Clojure integer 50, transform it to a church numeral, and then transform that back into a Clojure integer. And what I'm expecting to get here is 50. So let's evaluate this. And indeed, I got 50, which is pretty nifty. And another example, let's take the Clojure integer 2, transform that into a church numeral, and transform that into the string representation. So what I'm expecting to see is a string of the function of s that returns a function of z, which applies s twice. And indeed, we see here 2 applications of s. So this is working pretty nicely so far. So let's continue on. So we saw earlier that we can construct the nth church numeral for a given n. But that means that if we want a very high church numeral, we have to manually write it down or construct it somehow. And I'm looking for a mechanism that, giving a church numeral, I can construct the next church numeral. So that's called the successor function. So let's see here. We have this lambda term. I have an arbitrary church numeral. I apply it on s. I don't care what s is. I apply the result of that on z. I don't care what z is at this point. So if we just expand this church numeral into its body term, so we just see n applications of s. So let's do something. Let's apply s one more time on the right hand side, and we got this expression. Now it looks pretty weird, so let's remember I took the blue box here and I just applied s one more time on the blue box. And since the blue box here is equivalent to the red box, so I'm just going to replace the blue box here with the red box, and I get this. So I have this lambda term. This is an application. And what I want to do, I want to create an abstraction over this application. So I'm just going to abstract over s, cn, and z. And this is the definition of the successor function. It's a function of n that returns a function of s, that returns a function of z, and does all this fun inside. Okay, and you're probably like Tom, you're thinking to yourselves, what? So let's see a few examples in the REPL, and it's going to be a bit clearer. Excuse me. So again, the successor function here, it's a function of n that returns a function of s, that returns a function of z, and it does this calculation inside. So let's take the Clojure integer 50, transform that into a church numeral, transform that into its successor, and then transform that back to a Clojure integer. And what I'm expecting to see here is obviously 51, and indeed I got 51. And another example, let's take the Clojure integer 2, transform that into a church numeral, take its successor and transform that into a string form, and I'm expecting to see 3 applications of s, and indeed here I see 3 applications of s. So this is pretty nice, and we have another example here where we can see a few more of the successors of the first 4 church numerals. Okay, so what can we build on the successor function? So we can build addition. Why is that? Because let's look at a basic fact. When we say 1 plus 2, we mean add 2 to 1 or the second successor to 1. So the second successor to 1 is this lambda term. And we're seeing here that we're repeating a successor function. And the nice thing about church numerals is that they're an iteration mechanism. So let's iterate with our iteration mechanism. So if we want to apply the successor function twice, let's just use C2. This would apply the successor function twice on C1. So now we can abstract over C2 and C1, and this is the definition of addition in Lambda Calculus. It's a function of A, a function of B, and it applies the successor function B times over A. And here A and B are church numerals. So let's see a few examples in the REPL. So again, this is the definition of plus, and let's check plus and see what we get. So basically, I'm expecting here to see C11, which has 11 applications of s, and the integer 11. And indeed, we got the integer 11, and we can count here 11 applications of s. So this works pretty nicely. So now we can, given a church numeral, we can construct the next church numeral in the series, and we can do this technically until, or theoretically until infinity, and construct whichever church numeral we want, and we can add 2 church numerals together. So let's build on addition. So I have a question for you. What is multiplication? Well, it's iterative addition. Why is that? Because when we say 2 times 3, it means we add 2 to itself 2 times. Okay, so if we just want to iterate, we can use church numerals because they provide us with an iteration mechanism. So again, we said we're multiplying 2 by 3, so we're adding 2 to itself twice. We're going to use C2 to iterate twice. We're going to abstract over the 2 appearances of C2 and get this definition of multiplication. Now, if we try it in the REPL, it explodes in our face because we're getting class cast exceptions with the transformation functions here back into Clojure integers and back into string forms. And why is that? Well, basically it's because in plus our starting point was A, and in mult we create an application of plus on itself, and plus needs a starting point which should be C0. So let's fix the definition, and this is the correct definition for multiplication in Lambda Calculus, where you see we just add A B times to 0. So let's see that in the REPL. So again, here we see the incorrect definition of mult. Here we see the correct definition of mult. And let's check mult. And we can see that we're multiplying C2 by C3 here. And we should see here the result, which should be C6. So we should see 6 applications of S, and the actual number should be 6. Yeah, and indeed this works. We see here 6 applications of S. So this is pretty nice. Okay, so up to this point, we can construct sequential church numerals. We can add church numerals. We can multiply them. So let's build on multiplication. So exponentiation is just iterative multiplication. So we're going to do something very similar to multiplication, where here the exponentiation, we multiply instead of adding, and our starting point is C1 because 0 is the neutral element to addition in natural numbers, and 1 is the neutral element to multiplication in natural numbers. So again, we can see examples in the REPL of multiplication. So here when I'm raising 2 to the third power, I'm expecting to see 8. And when I'm raising 4 to the 0th power, I'm expecting to see 1. So let's check exp. And indeed, 2 to the power of 3 is 8, and 4 to the power of 0 is 1. So this is pretty nice. What can we build for? What can we build looking forward on exponentiation? Well, we can create super exponentiation, which is also called titration. This is the definition of super exponentiation. And in exponentiation, 1 is also the neutral element in natural numbers. And for example, if we see C2 super exponentiated to C3, that means we're raising 2 to the power of 2 to the power of 2. So basically, we're just creating a power tower, and we can do this over and over and over again and create the nth order of super exponentiation. And these are just numbers that just explode through the roof. And there are a few examples of super exponentiation in the code repository, and we're not going to see it right now. So I'm imagining up to this point, you're just like Lisa and Bart, and you're just like, man, I can't take this anymore. You've talked about functions and applications and abstractions and church numerals. And we can succeed church numerals, and we can add them, and we can multiply them, and we can raise them to the power, and so forth and so forth. But again, we haven't solved any problems. So what's next? What about data structures? What about logic? So numbers, operators, data structures, logic, that's the basic building blocks that we need in order to define problems and compute them or calculate them. So let's talk about ordered pairs, which are the most basic form of a data structure in Lambda Calculus. So this is a definition of a pair. It's a function that takes the first element, and then it returns a function that takes the second element, and then it takes a function, and it returns a function that expects a selector. And it applies on the selector the first element and the second element. I know this seems a bit weird. We're going to see an example in a second. This is the definition of the selector first. This is the definition of the selector second. It's pretty trivial. First, it takes the first element, takes the second element, and it just returns the first element. So let's see an example. So let's construct a pair out of 1 and 2. What do I get? So I'm just going to replace the text pair with the explicit lambda term here. Okay, I'm taking this entire abstraction and I'm applying it over 1. So I'm going to replace a with 1. So now I have a function of b. And I'm going to apply this lambda term on the number 2, on the church numeral 2. And then I get back a function that expects a selector, and it's going to pass into the selector the first element, and it's going to apply that on the second element, which is 2. And we can see a few examples in the REPL of this. So going back to the REPL, super exponentiation, yeah. So we have here a pair constructor. We constructed a pair. These are my two selectors, my first and my second. And let's apply my first on the pair of 5 and 10. What should I get? I should get 5. And let's apply the selector my second on the pair 5 and 10. What should I get? I should get 10. Indeed, I got 10. This is super nice. This is working just as expected. So now we have ordered pairs, and we can see that from ordered pairs, we can construct linked lists, where in each pair, the second element is another pair. And this is exactly how you make lists in Scheme. We can also create binary trees, because in a binary tree, the first element in a pair and the second element in a pair, they're going to be pairs themselves. And you see right how we can just construct all kinds of data structures just with pairs. This is pretty nice. Okay, so that's for data structures. Now let's talk about logic. So this is the definition of the Boolean true in Lambda Calculus. We see it's a function that takes the first thing, takes the second thing, just returns the first thing, false just returns the second thing. And this is not. Not takes a Boolean. If it's truthy here, then it would return the first thing, which is false. But if it's falsy, it's going to return the second thing, which here is true. And if we look at the definition of not in the Clojure source code, we see the exact same thing. If x is truthy, it would return the first thing, which is false. But if x is falsy, it would return the second thing, which is true. And this is pretty nice because now we see how a theoretical definition from the 1930s is implemented in a modern day programming language. This is the definition of AND. It takes two booleans. If the first one is truthy, it just returns the second thing, like AND in Clojure. But if the first boolean is falsy, then it returns here the second thing, which is false. And again, this is exactly the same thing as in Clojure, where here, if the test condition is falsy, then it would return the second thing, which is itself a falsy thing. But if it's true, it just returns the rest of the things evaluated. And this is the definition of OR. It takes two booleans. If the first one is truthy, then true is returned. But if the first one is falsy, then the second thing is returned, which in itself can be truthy or falsy. Again, just like the definition of OR in Clojure. Let's talk about mathematical predicates. So 0. This looks a bit heavy at first, so I'm taking a church numeral n. I'm applying it on this lambda term here, this function, and I'm applying the result of that on true. So why does this work? So let's see. This is the definition of C0. Again, it's a function of S that returns a function of Z that just returns Z. And if we look closely, we see here that Z, the second element, is true in the definition of the predicate 0. And S, which is the first element, is this lambda term, this abstraction here. So again, if n is C0, it's 0, then it just returns the second element, which is true, right? So I got back from the predicate, I got true, which is exactly what I want. But if it's not the church numeral, if n is not the church numeral C0, it's C1 or any other church numeral, then it's just going to apply this function on itself over and over and over again, and at the end it's just going to return false. Which indeed, because n is not C0, then I should get back false. So this is pretty nice. These are the definitions for greater or equal and lesser or equal. So let's look at it. So greater or equal. So we take A, we take B, and if B minus A is 0, then it's true. This looks pretty weird. So we have to remember something here. When I'm saying, when we have the minus here, we're actually talking about a function called monus. The definition of monus is like so. Monus AB is going to be A minus B if A is greater or equal to B, otherwise 0. So again, if A is greater or equal than B, and I'm expecting to get back true, then it means that B is lesser than A, and monus BA would return 0 by this definition, and I would get back true. So we're getting exactly what we're expecting, and with lesser or equal, it's just we flip around the order of the arguments, the order of the parameters in the body term, but not in the parameter order. So this works pretty nicely, and let's look at a few examples in the REPL. So we see here the definition of true, the definition of false, not, and, or. And we see here the definition of the predicate 0. And here I've constructed a test harness called if. If is going to take the test expression. It's returning a function of the do if true branch and returning a function of the do if false branch. And then it applies the test expression on the do if true branch and it applies that on the do if false branch. So here I'm asking, is C0 0? If it is 0, it's going to return the true predicate here. The true predicate here would return the first element which it gets, which is the Clojure true. So I'm expecting to see here the Clojure true when I evaluate it, and indeed I got the Clojure true. But if I ask if C1 is 0, I should get the Lambda Calculus false, which returns the second element which it gets, which is the Clojure false here. So here we should also remember, and we should understand, right here we're mixing Lambda Calculus and Clojure. This here is the Lambda Calculus, and the true and the false are Clojure. and that's because this is the way that I can actually play with the church numerals and all the logic and the predicates to actually get meaningful results back. Okay, so let's continue on. We have the definitions of greater, of lesser, of equality and inequality. We can see a few more examples of this in the REPL. So in order to calculate subtraction in Clojure, in Lambda Calculus, we need to use the predecessor function, and the predecessor function utilizes the ordered pairs that we saw earlier. I'm not going to develop this into the talk. You can have a look at it yourselves in the code repository. And again, the definition of the monist function here. So when I'm subtracting C2 from C5, I'm expecting to get the Clojure integer 3 back. And indeed, I got the Clojure integer 3. But if I flip around the order of arguments, I'm expecting to get 0 because 2 is lesser than 5, then I'm expecting monist to return 0. And indeed, I got 0 back. We have the few predicates here, so let's test. So is C3 greater or equal to C4? It isn't, so I'm expecting to get back the Clojure false. Indeed, I got back the Clojure false. Let's look at another example. Is C3 greater than C1? It is, so I'm expecting this expression to return the Clojure true, and it returned the Clojure true, so this is nice, and we can see all the other predicates and all the other all kinds of examples that you can play around with. Okay, so again, let's just sum it up. We've talked about lambda terms where we have variables, abstractions, and applications. We talked about church numerals, and then how we can construct in the next church numeral in the series with the successor function. And when we iterate over the successor function, we can add church numerals. And when we iterate over the addition function, we can create multiplication. And when we iterate over the multiplication function, we create exponentiation. We talked about data structures of ordered pairs and lists and trees. And we talked about logic of booleans and of predicates. And we can see that we have here all the basic building blocks that we need in order to calculate, or in order to define problems, mathematical problems in Lambda Calculus and calculate them. And just for the topping, we saw that iteration is the key mechanism here with Lambda Calculus. So if we have the predecessor function, as I've shown you earlier, we can iterate over the predecessor function to create subtraction, and we can iterate over subtraction to create division, and we can iterate over division to create logarithm, and so forth and so forth. So just a few related topics to sum up the talk. So fixed point combinators, if you've ever heard about the Y combinator, so that's a fixed point combinator, which basically means a fixed point combinator takes a non-recursive function and it transforms that into recursive ones. Circular data structures is another related topic, which is basically the same thing as a fixed point combinator, just seen from a different perspective. Multi-fixed point combinators, which take a bunch of non-recursive functions and returns one mutually recursive function. This is implemented in Clojure with trampoline. And basis for combinators, which remind of macros in Clojure. It's a pretty interesting topic, which you can also research. So that's it for today. Thank you very much for taking the time and listening to me. I hope you enjoyed it and that you've learned something new. Again, you can see all the code examples in the GitHub repository. You can contact me freely if you want to. And I wish you a very pleasant day, that you will enjoy other talks here in the Clojure North conference, and that you stay safe in these trying times.